Hello, my pretties, and welcome back to a wicked episode of Once Upon a Lecture. On today's episode, we're going to be learning about independent and dependent samples t-test. On our wicked agenda, we're first going to talk about the difference between two sample means. So you may remember in our previous lecture, we learned about finding the difference between the sample mean and the population mean. Now we're going to talk about finding differences between two sample means. After that, we're going to differentiate between independent samples and dependent samples. While we use the t-test for both independent samples and dependent samples, we have different formulas that correspond with each type of design. And that will take us directly into our third point of discussion, the different formulas. And I can't wait to show them to you. And to wrap up our discussion, we're going to revisit the 7-step method for hypothesis testing. Let's get started. So the first thing we'll talk about is finding the difference between two means. In the field of inferential statistics, a researcher is often interested in two things. The first one is obtaining data from samples, and the second thing is to generalize the findings from those samples to the population from which these samples came. Now we know, and we've heard multiple times, that it's practically impossible to collect data from entire populations. So what we often do is we take multiple samples from these populations. And so previously we discussed looking for differences between the samples and the population from which they came. So using hypothesis testing, we were able to test if the differences between the sample mean and the population mean were significantly different from each other. Remember, in research, values may differ from one another, but we must conduct statistical analyses to see if the differences are significant, to see if the differences that are in existence are actually significantly statistically different from each other. So, the analysis that we use to compare a sample to a population is called the one-sample t-test. But if we're going to talk about comparing the means of two different samples, we're going to have to learn about a different analysis. And this analysis is also known as a t-test, but we're going to differentiate for independent samples t-test and dependent samples t-test. So before we look at the new formula for these t-tests, we need to understand the difference between an independent sample and a dependent sample. So the first thing we need to understand is that independent samples are made up from specific types of participants. Independent samples is also known as between subjects design or a between subjects sample. So the participants in the sample are randomly selected from a larger population, and they are further randomly assigned to a specific condition. Now we know that the minimum number of groups we must have to conduct any type of statistical analysis is 2. The first group will typically receive the treatment or the independent variable, and the second group is often known as the control group or the one that receives no treatment of the independent variable or a different level or dosage of the independent variable. So when we compare these two groups, when we talk about random assignment, it means that everybody has a fair chance of being in the control group or if they're going to be in the treatment group. And the last and most important thing to understand about independent samples is that the participants are not related to each other in any way whatsoever. They are not siblings, they're not friends, they're not identical twins, and they definitely cannot be the same person. So basically everything that is opposite the independent samples design is going to be part of the dependent samples design. So another word for dependent samples is going to be repeated measures or within subjects. So if you think about the word repeated measures, the phrase repeated measures, it means that you are repeatedly measuring the same group or the same person over time. And within subjects basically means that you are going to be measuring the variance of the same person within him or herself. Whereas on the other hand, for independent samples, we have between subjects. So we're comparing different people to each other. But in dependent samples, we're going to be measuring the same group of people over time. So the same participants are going to be tested more than once, Or another instance in which we're going to use dependent design is if the participants are very closely related. So this could be, for example, a family. This could be a husband and wife if they have a very close relationship. And it can also be for identical twins. So the idea behind this is that any participants that are very similar to each other or may have experienced very similar types of environments, they're going to be very similar to each other and differ greatly from people who were not part of that environment and are not very close to them. And so testing those two groups together in the same formula or in the same test would actually convolute our results a little bit. So the reason we separate them is to make sure that we assess the variance for the different groups appropriately. If we think about it a little bit further, if you're going to measure the same people over time, this is going to cause the variance of the sample to be smaller, since we are reducing the possibility of individual differences. For example, if I was going to evaluate the strength of my power multiple times throughout the year, I would notice that I become more evilly powerful in October as it turns closer to Halloween. However, if I'm going to measure the strength of my power later in the year, for example, on Valentine's Day, I will still differ less from myself than if I were to compare the strength of my evil powers to, say, those of Maleficent or Regina, the evil queen. So in other words, when we compare ourselves to ourselves, we're going to differ from ourselves less than if we compare ourselves to somebody else. Therefore, because the variances would be smaller, we need to use separate formulas to test for this. So remember, when we collect samples from a population, the members of those samples typically have a certain amount of individual differences. And these differences increase the variance of our sample. If you think back to our discussion on measures of dispersion, you will remember that variance refers to how far the data points in our distribution differ from each other. And in order to show a significant effect of our independent variable on the dependent variable, we generally want the data points to have a smaller variance, because if the data points are close together, then it will be easier to see a trend or a pattern and to confirm that in fact there are significant results. If you have a distribution with data points plotted completely randomly and there's no clear way to see the trend, then that would probably indicate that there is no effect of the independent variable on the dependent variable. So all this is to say that generally in research, we want our variance to remain smaller if we in fact want to see significant differences. So individual differences of these participants are going to contribute to the size of our variance. Now, if you remember back to when we were learning about the t-test formula and the t-distribution rather, we learned that the t-distribution is similar to a normal or a z-distribution, but accounting for error. And so error and individual differences play a role in these formulas. And individual differences and error come from the participants themselves. So the formulas that are used to measure the differences between samples actually account for these differences between the groups. When we are interested in looking for differences among the same members of a group over time, the variance will be smaller. In other words, comparing someone to him or herself is going to provide less of a difference than comparing two unrelated participants to each other. So in order to account for the two types of samples that we encounter in our research, we have to use two separate formulas. One formula corresponds to each type of design and each type of sample. So let's take a look at the formula for the independent samples t-test. I can't wait to see your reaction. Wow, how wonderfully wicked and complex. But rest assured, we shall go through every step of this process and you will become a master of the independent samples t-test formula in no time. Let's take a closer look at the formula and really dissect the symbols to understand what is being asked of us when we're going to calculate an independent samples t-test. So if we look at the numerator, we know that X bar represents the average or the sample mean. Now, because we're comparing one sample mean to another, we're simply going to look for the difference between the two. And another word for difference is going to be to subtract. So in the numerator, easy peasy, we have the mean of sample 1 minus the mean of sample 2. If we look in the denominator, that's where the real party begins. So the entire denominator lives under the square root house. And so remember that keeping everything under the square root after you've solved all of the numbers and letters underneath it is a really important step. Sometimes because the steps are so long, we often forget that all of this was actually under the square root symbol. So please don't forget to square root the entire denominator. All right, so looking at the denominator, we know that n represents the number of people in our sample, and you see a small subscript with the number 1. So that's an indication that we need to look at the sample size for the first sample and subtract 1. So n minus 1 for the first sample, and then we're going to multiply it by s squared for the first sample. If you remember, s squared is the symbol for variance. So what we're going to do is we're going to calculate the variance for sample 1 and multiply it by what we see in the parentheses to the left of it. Once we do that, we're going to do the exact same thing for the second sample. So we're going to take the n of sample 2 and subtract 1, and we're then going to multiply it by the variance of sample 2. Once we do that, we're going to divide that numerator by the total number of people in sample 1 plus the total number of people in sample 2 minus 2. So all of that is going to be one entire unit. We are then going to multiply that quotient by the fraction 1 over n of group 1, 1 over the sample size of group 1, plus 1 over the sample size of group 2. So in other words, whatever calculations you're doing for the first sample, you have to do the same calculations for the second one. So none of these symbols should look new to you. They're just in a bit of a different order and kind of a concoction of symbols, kind of like a witch's spell, actually, now that I think about it. Now let's take a look at the formula for dependent samples t-test. Again, dependent samples t-test is going to be used if you have participants that are the same people being measured over time, or if you're going to be measuring people that are very, very related to each other. So the formula for calculating t when using dependent samples t-test looks like this. So again, the x bar represents the average, and now we have this new symbol for d. D is going to represent difference, and once again, difference is indicated by subtracting one value from another. Once we calculate the average of the difference, we are then going to multiply that by the square root of n. N represents the number of people in our sample. And oftentimes, because you're going to be using the same people more than once, you're only going to have one value for your n, as opposed to an independent samples t-test, you have one value for sample 1 and one value for sample 2. Now, all of this is going to be divided by the standard error of the difference. Now, you may remember calculating standard error when doing a one sample t-test. This is similar, but now we're going to be looking for the standard error of the difference. So how do we calculate standard error of the difference? Well, if we pull that apart, we can see that the standard error of the difference is equal to the square root of the sum of difference squared minus the sum of the difference then squared divided by n all over n minus 1. So if you're thinking to yourself, where have I seen this before? Well, you've probably seen pretty much the exact same formula when we calculate variance. The only thing is when we calculate variance, we have the sum of x squared minus the sum of x then squared. So instead of x, we now have a d, which represents the difference. So the d is going to represent the difference between the two different time periods that the participants were measured. So if we dissect this a bit further and try to put the symbols into words, we would say that t is equal to the average of the difference times the square root of the sample size divided by standard error of the difference. And the other formulas that we need to look at are the formulas for degrees of freedom. If you recall, when we were doing one sample t-test, we were using degrees of freedom n minus 1, and we only had one n value because we only had one sample. Now that we have two samples for independent samples t-test, you're going to do degrees of freedom are equal to the n of group 1 plus the n of group 2 minus 2. So in other words, you're doing n minus 1 of sample 1 plus n minus 1 of sample 2. For dependent samples, however, because we typically use pairs, or once again, people that are closely related, they're going to count as one unit or one participant representing one group of our sample. And so the degrees of freedom is equal to the number of pairs minus 1. So a pair can be me measuring myself 2 times, or it could be a set of identical twins, or it could be a husband and wife, etc. But basically, the pair that is very related counts as one participant. Now that we've taken a look at the two different formulas that we're going to be using for independent and dependent samples t-test, let's revisit the 7 steps. So whenever we do any type of hypothesis testing, we always use the 7 steps, regardless if it's a one sample t-test, independent samples t-test, correlation, ANOVA, regression, any type of statistical analysis will follow hypothesis testing and the 7 steps. So previously we tested significant differences between a sample and its population. Now we're going to test for significant differences between two samples. And so the first thing we need to do is identify whether our samples are independent or dependent. Here's kind of a good rule of thumb to go by. Unless you know that the participants are the same people being tested multiple times, or if the participants are related to each other in some way, then the sample will be independent. So in other words, a sample is independent by default. Unless you are told, or unless you collect data from people that are very closely related, like those two sisters in Arendelle, Elsa and Anna, they're practically the same person, that would be a good example of a dependent samples t-test. Now, if you consider comparing me to my less powerful sister Glinda, well, that's clearly independent samples. Even though we are sisters by blood, we have not one bone in our body that is in common. Naturally, I am the better sister. So that would be an example to use independent samples t-test. Even though we are related, we do not live in the same environment, we do not share any ideas, we barely see each other. So once you've identified if your design is independent or dependent, the rest of the 7 steps stay the same. The first step is to state the null hypothesis. Remember, the null hypothesis says that there are no differences between the sample of mean 1 and the sample of mean 2. The alternative hypothesis, which is step 2, says the exact opposite. So my alternative hypothesis would be that there are significant differences between the measure of sample 1 and the measure of sample 2. Step 3 requires no calculation or even writing whatsoever. You just set your alpha level to 0.05. Once again, this alpha level of 0.05 means that we are accepting a 5% chance of error. Now, step 4 is to set your rejection rule. It's that threshold that we're going to be using as a comparison to our t-computed value. So in other words, step 4 is asking us to find the critical t value for our sample. So previously, when looking up your t critical value, you needed one very important ingredient, and that is degrees of freedom. Now, remember, because you have 2 different formulas for degrees of freedom, you have to be careful that you choose the correct formula. So for independent and dependent samples t-test, we have 2 different formulas for degrees of freedom. So depending on which analysis you're conducting and which type of t-test you're going to be using, you are going to have to use the corresponding formula for those degrees of freedom. Step 5 is to calculate t using one of the 2 formulas that we just talked about. And once again, it's not up to you to just randomly decide which formula you want to use. It has to match the type of sample that you are actually measuring. Step 6 is to make your decision. In our decision, what we do is we compare the absolute value of the t computed value, which we've calculated in step 5, to the T critical value, which we found in step 4. Remember, negative numbers don't mean anything to us because we are going to consider the absolute value when making these comparisons. So if your T computed value is greater than your T critical value, you would in fact reject the null. That would be your decision. And if you reject the null, you are left with the alternative. And the alternative says that there is a difference between the groups. If the T computed value is smaller than the T critical value, then that means you would fail to reject the null. In other words, you would keep it. And if you fail to reject the null, you are concluding that there are in fact no differences between the groups. And last but not least, my favorite part is to write your conclusion. Now remember, when you write your conclusion, after making your statement, it is imperative that you include the statistics after you make your statement. So that formula for how to write a proper conclusion would be to state whether there is a difference or there is not a difference between the samples, comma, T parentheses degrees of freedom is equal to your T computed value that you calculated in step 5. And if you reject the null, then you have comma P less than 0.05. But if you fail to reject the null, you have comma P is greater than 0.05. So those are some things to be aware of when you're writing your perfect conclusion statement. All right, I'm ready to try some wicked examples. Let's do it. An experiment was performed to measure the effect of sleep deprivation on wickedness. 20 munchkins from Oz were randomly selected from the meadows and arbitrarily assigned either to a sleep deprivation group or to a control group. The participants in the sleep deprivation group were kept awake for 24 hours. The members of the control group had a normal night's sleep. Participants were then asked to create a potion that would break the heart of their beloved. The time it took each participant to complete the potion was recorded. Shorter completion time indicated more wickedness. Determine whether or not the groups differ significantly. So let's take a look at the data that we've collected. So in the first column, we see the time in seconds it took the sleep-deprived group to complete the potion. And in the second column on the right-hand side, we have the control group, the one that got a normal night's sleep. And we see the time in seconds that it took them to complete the potion. So the first question is this dependent or independent design, and how do you know? If you're thinking to yourself, this is an independent design, then you are absolutely right. What makes it independent are the fact that we have no information that the munchkins were related to each other in any way. We also know that they were randomly selected and randomly assigned to either the sleep-deprived group or the control group. So all signs point to the fact that this is an independent samples design. So the question is, what is our sample size? So we have 2 different groups and we have 2 samples. So in total, we have 20 munchkins that participated, but we have N of sample 1 is equal to 10 and N of sample 2 is equal to 10. Do both samples always need to have the same number of participants? No, but it's generally better because then you have equality, and if you have differences in your average or in your variance, it won't be due to the fact that one group had more participants or data points than the other. So what is our independent variable? Remember, in the example, I was curious to see if sleep deprivation would in any way affect the wickedness of these munchkins. In other words, if they don't sleep, will that inhibit them from completing the potion more quickly? So in this case, our independent variable is sleeping condition. The first group would be the one that didn't sleep, the sleep deprived, and the second group, or the second level, would be the one that had a normal night's sleep, aka the control group. So what is the comparison that we are making? Well, we're comparing how quickly those that were sleep deprived were able to complete the task of creating a potion compared to the amount of time it took the control group to complete the potion. So in other words, our dependent variable, or the thing that we are measuring, is the amount of time, recorded in seconds by the way, that it took these groups to complete the task. So we have an independent samples design, because the subjects are not related to each other in any way. We have two levels of the independent variable. So we only have one independent variable, which is sleep condition, but it has two possible options, sleep deprived and control group. And the dependent variable that we're measuring is the completion time in seconds for completing the potion. So because this is an independent samples t-test, we will be using the formula for independent samples t-test, the one illustrated here. Given the symbols in the formula, it looks like we need to find the means or the average of both of the samples, and we also need to calculate the variance for both samples. So let's get started doing that. We know that in order to find the mean for each group, we need to find the sums of all the data points and divide them by n, the total number of people in our sample. Once again, we have two samples, two n's, so we need to calculate two different sample means. If we look at the sum of the first column for the sleep-deprived group, we get a total of 147. If we take 147 and divide it by 10, the number of people in our data set, we get an average of 14.7. We're going to do the same thing for the control group. Once we add up all of the seconds in the control group, we get a total of 87. 87 divided by its corresponding n, which is also 10 in this case, is going to give us the sample mean of 8.7. So, in other words, we have a sample mean of 14.7 for sleep-deprived group, and we have a sample mean of 8.7 for the control group. By looking at the averages, it looks like the control group took less time on average to complete the potion. So even though we see a difference between 14.7 and 8.7, we can't be fully sure that the differences are significant until we put it through the 7-step process. So now that we've calculated the averages, we need to calculate the variance for each group. Let me remind you, the formula for variance looks like this. S squared, or variance, is equal to the sum of x squared minus the sum of x, then squared, divided by n, all over n minus 1. So, in order to calculate the sum of x squared, we actually need to take each value and square it first in order to then sum them together. And again, we need to do this twice, once for each sample. So we need to find the variance for the control group, and we need to find the variance for the sleep-deprived group. Once we do that, we have 10 times 10 is 100, 15 times 15 is 225. So we have to go down the row for the sleep-deprived group and down the row for the control group. So once we do that, these are the numbers that you should end up with. After you've calculated the squares of each score, we then need to get some totals. We need to get the sum of x squared for each sample. So we're going to take the sum of x squared for the sleep-deprived group, which is going to be 2,563, and we're going to take the sum of x squared for the control group, which is going to be 985. Now, it looks like we have all of our values to calculate the variance for each group. So let's go ahead and do that. So here are the values that we know, that we've just calculated. We know the means, we know the sum of x, we know the sum of x squared, and we know the sample size for each of the two samples. So let's take a look at the variance for the sleep-deprived group first. We know that 2,563 is going to go in place of the sum of x squared. We're going to subtract 147 squared over 10, all over n minus 1, which is going to be 9. So it will look something like this. If we simplify 147 squared over 10, we get 2,160.9. So after we subtract the numerator and divide by the denominator, we get a variance of 44.68. 44.68 is the variance of sample 1 for the sleep-deprived group. Now let's take a look at the variance for sample 2. So we're going to do the same exact thing, and now we're going to plug in the values that we've calculated for sample 2. If we take the sum of x squared, we have 985. 985 minus 87 squared over 10 divided by 9. So you just plug in the values where they go into the formula, and once you subtract the numerator and divide by the denominator, you get a variance of 25.34. So 25.34 is the variance for the control group. Now that we have all of the elements of our formula, we can actually plug it in to our t computed value. So let's take a look how we'll do that. Again, these are the values that we've just calculated. We know that the variance of the first group is 44.68. We know that the variance of the second group is 25.34. Both samples had 10 participants, and we can also see that the mean of group 1 is 14.7 and the mean of group 2 is 8.7. So this is our t computed formula for independent samples. So now all we need to do is put the numbers in place of the symbols from the formula. So x1 will be represented by 14.7 and x2 is going to be represented by 8.7. n minus 1 of the first group is going to be 9 because 10 minus 1 is 9. And we're going to multiply 9 by the variance of group 1, which is 44.68. After you've gotten this product, you're going to add it to the sample size of group 2 minus 1, which will also be 9 because we also had 10 people in the second sample. And we're going to multiply that by the variance of sample 2, which in this case is 25.34. All of that is going to be divided by n of group 1, which is 10, plus n of group 2, which is also 10, so that's 20, minus 2, which is going to give us 18. Once we do that part in the parentheses, we move over to the right-hand side and we see 1 over n of group 1, which is 10, plus 1 over n of group 2, which is also 10. So you will have 1/10 plus 1/10. Once we've calculated that, don't forget to take the square root of that entire denominator. Once I plug in the numbers in place of the symbols, I get 14.7 minus 8.7 in the numerator, and all of that exciting stuff in the denominator. So if I simplify this further, 9 times 44.68 will give me 402.12, and I'm going to add that to 9 times 25.34, which is going to give me 228.06. After I add those together, I'm going to divide by 18 and multiply by 1 over 10 plus 1 over 10. Further simplified, I see that that is the square root of 35.01 times 0.2 in the denominator, and 6 remains in my numerator. If I take 6 over the square root of 7.002, I am left with the t-value of 2.27. So this t-value is essentially what we would do in step 5 of our 7-step process. 2.27 is our t computed value. So now let's move on and complete the rest of our 7 steps. Step 1, state the null hypothesis. Well, we know that the null hypothesis means that there are no differences between the groups. So in other words, there is no difference in potion completion time for the munchkins who were sleep deprived and those who were not. Or another way you could say this is that the munchkins who were not sleep deprived completed the potion in the same amount of time as the munchkins in the control group. So the alternative hypothesis would be the exact opposite, would be to show that there is a significant difference in potion completion time for the munchkins who were sleep deprived and those who were not. And according to our averages, we can see that those who were not sleep deprived actually completed the potion more quickly. So far, it looks like the alternative hypothesis is the one that played out in the data. But again, we have to test it to see if the differences are significant. Step 3 is setting alpha to 0.05, in other words, accepting 5% error. Step 4 is to set the rejection rule, in other words, to find t critical. Now, because this is an independent samples t-test, we know that the proper formula for degrees of freedom is going to be n1 plus n2 minus 2. So we calculated a similar situation when we were just calculating our t-value. So we know that 10 participants were in group 1 in the sleep-deprived group, and 10 participants were in the control group. 10 plus 10 is 20, minus 2 gives us 18. So what we need to do is we need to go to the t-table, the same one you used for the one sample t-test, but this time you're going to be using different degrees of freedom. Instead of n minus 1, you're going to use n1 plus n2 minus 2. We've calculated that our degrees of freedom are equal to 18. Now remember, because we've set alpha to 0.05, it means we're going to be looking for the t-value at the 5% error level. By looking at the chart, we can see that that value is in fact 2.1009. So 2.1009 is representing our t critical value at 18 degrees of freedom. Moving on to step 5, which is to compute t. We've just calculated that, and we found that t is equal to 2.27. So now the moment of truth. We make our decision. We remember that the way we make this decision is by comparing the t computed value, which is 2.27, to the t critical value, which is 2.1009. If the t computed value that we've calculated from our data is greater than or equal to the t critical value, our decision will be to reject null and conclude that there is a difference. If we see that our t computed value is smaller than the t critical value, we conclude that there are no differences because our decision would be to fail to reject the null. So by looking here, is 2.27 greater than, equal to, or less than our t critical value? Well, it looks like the absolute value of our t computed value is in fact greater than the absolute value of our t critical value, so our decision will be to reject the null. And ultimately, our conclusion will say that the munchkins that were sleep deprived did not take the same amount of time to complete the potion as those who were not. And here's the really important part. You put your comma, t degrees of freedom, which are 18 because n1 plus n2 minus 2, is equal to your t computed value, which is 2.27. And because we've rejected null, we're going to say comma p, the probability of making an error, is less than 0.05. So once you've written this beautiful conclusion statement, you are in fact done. So going back to the original question, does sleep deprivation affect wickedness? Or in other words, does sleep deprivation affect one's ability to concoct potions more quickly? The answer would be yes, because we saw that the average completion time for those who were not sleep deprived was in fact significantly shorter. All right, let's try another example. The wizard asked 13 members of Oz to vote for their next leader. All the members, or participants, listened to a speech by the Wicked Witch, myself, and by Glinda, the Good Witch. Then the participants were asked to rate our speeches on a scale from 1 to 30. The higher the number, the more satisfied the participants felt with the speech. Determine which witch's speech was more successful and determine whether or not the difference was significant. Honestly, it's like such an easy win here, but humor me and we'll just look through the data that came back from this. So here we can see the data that's been collected by the wizard. 13 participants listened to both my speech and Glinda's speech about our visions for the future of Oz. The numbers that we see here represent the ratings that the participants gave to each of our speeches. So if we think about it, we can see that 13 participants listened to both speeches. In other words, they were exposed to the same thing at different times. So the question I have for you is this independent or dependent samples design, and how would you know? So our example didn't say anything about random assignment. It also didn't say anything about participants being separated into two different groups. What it did say is, in fact, the opposite. We can see that the same participants were exposed to both levels of the independent variable. In other words, both types of speeches. So this sounds like it's going to be a dependent samples t-test because it's the same people being tested over time. So what is our sample size? We know that our n is represented by the number of pairs. Pair meaning we had two different speeches that were listened to, but how many participants evaluated those? The answer would be 13. So n represents 13. What is our independent variable and how many groups or levels does it have? Well, clearly our independent variable is the speech. Was it my speech that was more effective or was it Glinda's speech that was more effective? And so we have two groups. The comparison that we are making is in ratings or evaluation of the two different speeches to see who will be the more effective leader. And so our dependent variable in this case would be the ratings for our speeches. Because this is a dependent samples t-test, we will be using this formula. The average of the difference multiplied by the square root of n divided by the standard error of the difference. Before we get into the intricacies of the standard error of the difference, what we need to do is calculate the difference for each group. Another word for difference is subtraction. So what we need to do is compare and subtract, I should say, the score of the Wicked Witch from the score of Glinda the Good. Once we do that, we'll proceed further to calculate the standard error of the difference. So if we start calculating the difference, you're going to want to go ahead and make yourself a table with a column labeled D for difference. Now the difference is going to be the score of the Wicked Witch minus the score of Glinda the Good Witch. So we see 26 minus 23, 13 minus 16, 10 minus 6, 24 minus 19, etc., all the way until the 13th participant. But we also need to square each difference since this value is going to be used to calculate the standard error of the difference in our t formula. If you recall, that's the one that looked like the sum of d squared minus the sum of d then squared divided by n all over n minus 1. So in order to find the sum of the difference squared, we need to create a d squared column. So the d squared column is essentially the value we have in the d column for the difference, that number squared. So for example, 26 minus 23 gives us a difference of 3. 3 is the difference that I'm going to square and place in the d squared column. 3 squared is going to give me 9. Then I have 13 minus 6. 13 minus 6 gives me negative 3, but once I square negative 3, it becomes positive 9 as well. So I'm going to square every difference in the d squared column until I get all the way down to the 13th participant. So now that I have these values, what I do need to do is tally them up, right, and get the sum of all of these columns. So I will need the sum of d, and I will need the sum of d squared. One other value that I'm going to need is the average of the difference. So similar to how we calculate the average of any set of data, because I need the average of the difference, I'm going to take the sum of the difference total, which is 31. I'm going to add up all of the differences I have, and I'm going to divide by the total number of data points I have, which in this case is 13. So if I calculate the mean of the difference, I have 31 divided by 13, and that gives me 2.38. So in other words, the average of the difference is going to be 2.38. I can also see that the sum of the difference is 31, and the sum of the difference squared is 199. So now that we have all of the elements of this formula, we can actually plug them in and calculate our t computed value. So here are the values that we know that we've just calculated. The average, the sum of d, and the sum of d squared. Here's what that formula looks like once again. So we have the average of the difference, which would be 2.38. We know that n is 13, so we're going to multiply by the square root of n. But the sum of the difference is the part that we actually haven't calculated yet. So the sum of the difference is equal to the square root of the sum of difference minus the sum of difference squared over n, all over n minus 1. So, if we simplify that further, we know that the sum of the difference squared is 199. If I subtract that from 31 squared, because 31 is the sum of the difference, and I divide that by 13, I'm going to then divide all of that by 13 minus 1, which is going to give me 12. So this is what I'm going to see. As I simplify that further, I can see that 31 squared over 13 is going to give me 73.2. So I simplify it further and I see 199 minus 73.2 divided by 12. Once I calculate this quotient, 199 minus 73.2 over 12, I'm going to get 10.42. And remember, don't forget that square root. So the square root of 10.42 gives me 3.23. But we're not quite done. Remember, 3.23 is the standard error of the difference. This is the number that's going to go in the denominator of our dependent t-test formula. So let me just remind you, we said that the average of the difference was 2.38 multiplied by the square root of 13 divided by 3.23, which is the standard error of the difference that we've just calculated. Once you simplify that, you ultimately end up with a t-value of 2.66. So 2.66 represents your t-computed value for the dependent t-test formula. In other words, this is step 5 of those 7 steps. This is the value that we're going to be comparing to the t-critical value we find in our t-table chart. So let's backtrack a little bit and go back to completing our 7 steps. So step 1, state the null hypothesis. Well, again, this was all about a speech that I gave compared to the speech that Glinda, my sister, gave, and we wanted the people of Oz to vote for which speech was more effective to ultimately determine who is the rightful leader of Oz. So, the null hypothesis would be that there is no difference in ratings for the speeches of the 2 candidates, right? The null hypothesis says that the 2 groups are the same. If groups are the same, then there are no differences. The alternative hypothesis would say that there is a significant difference in ratings for the speeches of the 2 candidates. So the alternative hypothesis is just the opposite of the null. If the null says there are no differences, the alternative would say that the differences do exist. Step 3, as usual, just set alpha to 0.05. This is typically the default measure, the default accepted error level. Could you change it and make it more strict to 0.01? Absolutely. But unless we are told to do so, we just use 0.05 as the default. So step 4 is where things get tricky. And again, you need to be very careful that you pay attention to how you calculate your degrees of freedom. We know that degrees of freedom are needed to look up the proper t-critical value in our chart. But because we have 2 different types of designs, we also have 2 different types of formulas for degrees of freedom. Because this is a dependent samples t-test where we're measuring the same people over time, we have to use the formula number of pairs minus 1. Because we know that our n and the number of pairs in this current sample is 13, 13 minus 1 gives us 12. So we're going to take this number 12, our degrees of freedom, and we're going to go to our t-table chart and locate which t-critical value is at the 0.05 error level for 12 degrees of freedom. If we look in the chart, we can see that that value is 2.1788. So this is the t-critical value that we are going to compare to our t-computed value when making our decision about the null. Step 5 is to compute t. We just did that and we found that t is equal to 2.66. Step 6 is to make your decision. Once again, we have to compare the absolute value of t computed to the absolute value of t critical. Is the value of t computed greater than or equal to t critical? If it is, then we reject the null and we conclude that there is a difference between the groups. If the t computed value is less than the t critical value, then we conclude that there are no differences because we fail to reject the null. By looking at this example, we can see that the absolute value of 2.66 is in fact greater than our t-critical value of 2.1788. So our decision will be to reject the null. After we make our decision, we write our conclusion. In this case, it would be that the ratings for the speeches of the Wicked Witch and Glinda the Good were significantly different. Comma, T with the degrees of freedom. In this case, we had 12 degrees of freedom. That's going to be equal to your T computed value of 2.66. And you're going to put a comma, P less than 0.05 because you've rejected the null. Remember, if you fail to reject the null, then P becomes greater than 0.05. All right, that's it. We made it through this wickedly complicated lecture on independent samples versus dependent samples t-test. I know the formulas may look a little overwhelming and intimidating, but the truth is you know exactly how to calculate them because all of the symbols that exist in the formulas you've already been calculating for months by now. So just take your time and just walk through each step slowly without rushing, and then you should have no issues completing any exercises relative to independent samples or dependent samples t-test. As always, drop some questions in the comments below if you have any, and I'll be happy to answer them for you. Thank you so much for watching, my pretties, and I hope you enjoy the rest of your week ahead. Ta-ta!